Welcome to The Explainer. If you look down at the solid ground beneath your feet, it's pretty crazy to think about how it actually sustains life. Today, we're translating the fascinating hydrogeology of aquifers to discover how this seemingly impenetrable rock below us is, in reality, acting as a massive, dynamic water sponge. Okay, let's dive right into this and uncover the hidden mechanics that keep our world hydrated. To really grasp this, we first need to completely shatter a very common myth. When we hear the word groundwater, I bet a lot of us instantly picture these massive, echoing underground lakes or maybe roaring subterranean rivers, like something straight out of a fantasy novel. But that's rarely the reality. We really have to ask, where does our drinking water truly reside? The answer isn't in giant caverns, but rather hidden deep within the microscopic architecture of the rock itself. All right, Section 1, porosity, storing the water. To wrap our heads around this hidden world, we actually need to shrink our perspective way, way down to the microscopic level. We need to see exactly how solid rocks manage to store any water at all. Just look at this block of dry sand. Looks completely solid, right? But pour some water on it and notice how the liquid perfectly fills those tiny, almost invisible void spaces between the individual grains. Suddenly, you've got a fully saturated block. The rock isn't melting, it isn't dissolving, it's literally just acting like a dense sponge, taking full advantage of all that empty room hidden within its structure. So the big takeaway here is that porosity is really just a mathematical index. It tells us the exact percentage of a rock's total bulk volume that is purely empty space. Think of it this way. If you've got a cubic meter of sand and 40% of that is just empty space waiting to be filled, well, your porosity is 40%. It's the absolute definitive measure of how much water an underground formation can actually hold. And it's wild how visually obvious the storage difference becomes when we just tweak the physical makeup of the rock. Take perfectly round, loosely packed grains. Because of that uniform shape, they just can't fit tightly together, right? So they leave these large open voids. Bam! Greater porosity. But mix large and small, tightly packed grains together, the tiny pieces act like puzzle pieces, filling in the gaps between the larger ones, which severely reduces the amount of empty space available for water. Which means the total storage capacity of our underground rocky sponge isn't just random. It is strictly dictated by 5 key physical characteristics. We're talking about the shape of the grains. Flake-shaped grains pack super tight, while rounded ones leave gaps. It depends on sorting and packing, like we just saw. Plus, we have to factor in the degree of cementation and compaction over millions of years. If these grains are heavily cemented together by minerals or absolutely crushed under massive geological weight, your storage space is going to plummet. Moving right along to Section 2, permeability, moving the water. Because here's the thing, storing water is really only half the battle. Now we have to look at the incredibly complex mechanics of actually moving it. For a rock to be useful to us, those microscopic pores can't just exist in total isolation. They absolutely must be interconnected. Permeability is simply the measure of how easily a fluid flows through a rock when there's a pressure difference. Those void spaces have to be linked together like a microscopic highway system, and those highways better be wide enough to let the fluid actually move freely. And that brings us to this fascinating hydrogeological brain teaser known as the shale paradox. You'd probably assume that a rock with high porosity naturally lets water flow easily. Actually, scratch that. It's completely false. Take shale, for instance. Shale can be highly porous, meaning it has a massive amount of empty void space to store water. But because those microscopic pores are just too tiny and completely disconnected from one another, it is practically impermeable. It literally acts as a massive roadblock to water flow. No way through. Honestly, prepare to have your mind blown by the staggering geological scale we are dealing with here. When we measure how fast water drops just 1 single meter through different sediments, the contrast is unbelievable. Water zips through the large interconnected pathways of gravel in an incredibly fast 2 minutes. But ask that exact same water to travel that exact same 1 meter distance through heavily packed clay, it is going to take a painstakingly slow 200 years. Just think about that. 2 minutes versus 2 centuries, all based purely on the microscopic permeability of the dirt. All right, Section 3, yield versus retention. So now that we know water can actually move through these interconnected pores, we really need to face the human-scale reality of trying to extract it, which brings up a super critical question for society. If we know an aquifer holds millions of gallons of water, can we just sink a well and pump all of that stored water right out of the ground? Well, the tension here is that just because a rock formation holds a massive amount of water, it absolutely does not mean it's willing to give it up to our wells. To understand why, we have to look at what is basically the ultimate underground tug of war. On one side, we've got gravity, effortlessly pulling water down into our wells. That usable water is called the specific yield. On the flip side, we have the rock itself fighting back. It uses molecular attraction, surface tension, and capillary forces to stubbornly trap water inside its tiny pores. And that water, the stuff the rock absolutely refuses to let go of, is called specific retention.
You can really see specific yield in action here. We start with this large, fully saturated block of aquifer material, but notice that only a precise, much smaller fraction of water actually drips out the bottom. That dripping water right there is the specific yield. It's the portion that defeats surface tension, drains by gravity, and actually becomes usable groundwater for us. The rest of it, permanently locked within that saturated cube.
Which leads us to Section 4. Finding the perfect aquifer. Let's actually put all this textbook theory we've just learned into practice and solve a little real-world puzzle to figure out exactly where we should drill a well. Imagine we're surveying land and we pull up two soil samples, sample A and sample B. Both have the exact same total volume of 1 cubic meter, and impressively both boast the exact same porosity of 35%. So on paper, they hold the exact same amount of water. But after testing gravity drainage, sample A releases 0.25 cubic meters of usable water, while sample B only gives up 0.10 cubic meters. With both holding the same amount initially, which site is actually giving us the water we need to supply our town?
Well, sample A is the clear winner, for sure. It yields 2.5 times more water. Even though sample B has great porosity, its specific retention is just way too high. It holds onto its water way too tightly. This perfectly illustrates that a perfect aquifer requires a really delicate balance. It needs high enough porosity to act as a massive storage sponge, absolutely, but that has to be combined with high permeability and high specific yield to actually let that water flow freely out of the rock and into our wells. So the next time you look down at the solid ground you're walking on, I want you to keep this invisible world in mind. The water beneath us isn't just some endless underground lake. It's a finite resource, slowly creeping through a microscopic maze. And I'll leave you with this final thought to ponder. As global populations keep growing and our demand for water skyrockets, are we extracting this hidden ancient water faster than the decades or even the 200 years it might take to replenish? Thanks for exploring the depths with me on this explainer. Keep wondering, and we'll catch you next time.